Titrating NaOH with KHP and H3X by Cailin, Kelly, and Tom Kim. So in titrations, neutralization reactions are used to determine the molarity of an unknown acid or base solution using an acidic or basic solution of a known concentration, and they have a lot of real-world applications. They can determine certain concentrations of chemicals, or they can determine the amount of substances in food, and they have a lot of applications in the lab and research too. So the purpose for this particular experiment was to give us practice in making solutions and doing the calculations, and obviously to learn how to do titrations, which are a very important lab technique. And our objective in the lab was to standardize or find the exact molarity of our NaOH solution, and then to determine the molarity of a solution of H3X, which is a triprotic acid, and to eventually find the molar mass of H3X. And we used a lot of materials in this lab. Here's our setup, which looks somewhat like this, except our beaker will have solution and indicator in it and be under the burette, which will be full of NaOH. So we have a funnel, a stand and a clamp, a burette, an Erlenmeyer flask, a beaker, a volumetric flask, a weigh boat, a stirring rod, phenolphthalein, and our NaOH solution pictured here. And for more materials, we used two different balances with differing numbers of significant figures. We also used sodium hydroxide, KHP, and H3X, which was our unknown acid. So the first part of our procedure was to make and standardize our NaOH solution. So to do this, we would first make 250 milliliters of 0.4 molar, approximately, NaOH solution in a volumetric flask, which we later stored in a plastic bottle. And after we'd practiced using the burette, we dissolved between 1 and 1.1 grams of KHP in water in our Erlenmeyer flask, and we added our indicator, and then we titrated the NaOH and the KHP, and we did this until the liquid turned a light pink, and it stayed that way after stirring, and this is the end point of our reaction. And using our measurements from how much NaOH we'd used and the amount of grams of KHP, we could determine the exact molarity of our NaOH solution. The next part of our procedure was to find the molar mass of H3X. So we dissolved between 1 and 1.1 grams of H3X in water in our Erlenmeyer flask, and again added indicator. And once again, we titrated the NaOH solution into the H3X solution and stopped at the light pink color, or the end point. And then we used the amount of NaOH we used and the amount of grams of H3X to calculate H3X's molar mass. Some important procedural notes to be aware of are that we have to use the maximum amount of sig figs possible, and that since NaOH can severely damage your tissues because it's very basic and very corrosive, we would have to wash it off as soon as we got any on our hands, because since we were using a funnel, some spillage was inevitable. And a very important thing to be aware of is the color pink that your indicator turns. Phenolphthalein will change color at the end point of our titration. In this case, it happens at about a pH of 8.0 to 9.8. But we want to get a really light shade of pink, because that's when the endpoint starts. And if we get a darker shade of pink, we will have used extra base, and therefore our calculations will be very off. In fact, we had to throw away some trials because of this.
At this time, we will talk about the calculations involved in this lab. So first, given that we have to make 250 milliliters of a 0.4 molarity sodium hydroxide, we can calculate this. We could calculate the mass of solid sodium hydroxide needed to make such solution by the equation below, which involves, first of all, the given 250 milliliters of the whole solution. And first we have to convert this milliliters into liters, because when we multiply this to the molar mass of sodium hydroxide, it's always in liters. So we convert it to liters and then multiply it to the molarity of sodium hydroxide that we want, and finally multiply the molar mass of sodium hydroxide to get 4.0 grams sodium hydroxide. Next, we can calculate the molar mass of KHP by adding the mass of individual elements involved in KHP. And finally, the molarity of the sodium hydroxide solution is calculated by 1.100 grams of KHP multiplied to 1 mole KHP over 204.222 grams of KHP, which is the molar mass of KHP that we got in this step beforehand. And finally, multiplying the 1 over 15.05 milliliter sodium hydroxide, which is the volume that we acquired, the volume that was needed to complete the titration. And finally, we convert the whole thing to liters. And at the end, we get 0.3579 molarity of sodium hydroxide for the data that we got from trial 1. To end the lab, we must make a final calculation of the molar mass of the unknown substance. And of course, we're going to be using trial 1 data, most of which we just calculated in the slide before. And in this calculation, we start out by converting milliliters to liters, and then we would use the molar mass and the molarity of NaOH, and then we would get the mole ratio of 3 moles sodium hydroxide to 1 mole of unknown substance to convert so that our final solution pertains to the unknown substance. And finally, we get 206.9 grams per mole. Our data table shows what we got in each of our trials and also the averages per trial, and this is what our data looked like. One important thing to note in looking at our data alone is that we were table 2 in D period, and on it says that we got 209.0 grams per mole of the unknown substance. However, on the previous slide, you might have noticed that our average was actually 208.4 grams per mole. What happened here was the day we had to submit our information into the spreadsheet, we made a calculation error in trial 1, and what ended up happening was the molar mass for trial 1 was calculated to be around 207.5, which is definitely higher than the 206.9. When we redid our calculations, we found out that there was this error, and although the molar mass is 209.0 grams per mole in the class data, what we actually should have gotten is displayed on the previous slide data table as 208.4 grams per mole. Data analysis. So by using the 3-step test, we got that D period group 11 and G period group 5 data were eliminated because they were outliers, and the mean molar mass of the unknown substance was 212.8 grams per mole, and the median molar mass of the unknown substance was at 211.0 grams per mole. And finally, our average molar mass, as you probably can recall, was 208.4 grams per mole. Since our average is close to the class average, in fact, it's within 1 standard deviation, we can claim our data as being fairly accurate. And by looking at the fact that our data was also 1 standard deviation within the median, we can also claim that our data was fairly precise. We found 2 errors, and the first one is with weigh boats. When we transfer substances from weigh boats to either flask, beakers, or any other kind of container, either any kind of substance that is in the weigh boat is most likely to continue to stay in the weigh boat. And in our lab, it was either the KHP or the unknown substance. And because not all of it would get off from the weigh boat into the solution, our measured mass of KHP and or the unknown substance were slightly higher than the actual value. Therefore, our calculated molarity of sodium hydroxide and our molar mass of the unknown substance were calculated to be higher than they actually were. The second error that we found in our lab relates to the shade of pink that we must get when we titrate any kind of substances. We have to get this lightest shade of pink possible because this occurs at the end point of the reaction. However, getting the lightest shade of pink is near impossible to do, and we will always have extra sodium hydroxide. Therefore, the volume of sodium hydroxide used to neutralize is actually lower than what we measure. This causes our molarity of sodium hydroxide to be higher than what we calculated, and therefore our calculated molar mass of the unknown substance is also lower than what it actually is.
So, in conclusion, we used a titration to determine the molar mass of an unknown, and even though our data was affected by the errors we described previously, everyone who did this experiment faced the same errors, so our data is not less accurate or precise because of it. Rather, everybody's data has been shifted altogether. So, titrations are very useful in our lab as long as we know the molar mass or molarity of at least one of our substances or solutions, and it has many real-world and research applications, and since titrations are widely used in science, we will most likely be doing them again. Finally, here is our bibliography.